Alright, everyone, this is section 6.5, the last lesson in chapter 6. Do you like green Skittles? Let's dive in. So, in 2021, Skittles made the right move when they changed the flavor of the green from sour apple back to lime. I guess I agree with that. A party-sized bag has 1,200 Skittles, and 20% of those are green. Mr. Wilcox takes a random sample of 100 Skittles to have as a snack. Seems like a pretty big snack. Whatever. Okay. Is it binomial? So I've pretty much written down bins, because remember binomial is B-I-N-S, bins. It is binary because a success would be getting a green and failure would be not getting a green. Independent, this one is worth a discussion, okay? Does each Skittle affect the probability of the next Skittle? And the answer is that we're good here. Each Skittle does not affect the next. I should say this carefully. Each Skittle does not significantly affect the probability of the next Skittle. And the reason is because the sample size here, or the population size, is so large, and I'm only taking out 100 Skittles. So the probability is not changing very much, even though I'm not replacing the Skittle. The cutoff here is 10%. 100 is my sample size, and that is less than 10% of 1,200. Let me just say this. Let me show you a brief example. Let's say the first Skittle was green. The probability of it being green is, well, let's see, you might need a little calculator to help me through here. It says, what, 20% of the Skittles are green? So 20% of 1,200, so 240 of the Skittles are green. So let's say the first one was green, okay? Well, that would be 0.20, right? So let's say the first Skittle was green. What's the probability that the next Skittle is green? Probability of green again. Well, now there's 239 Skittles because I took out the first green Skittle. And the next Skittle is out of 1,199. What I'm asking here is, not putting that Skittle back, did that make a substantial difference in the probability? I mean, look at that. The answer is no. It's 0.199. So we're okay to keep taking these Skittles out and not put them back. You see the not replace them, because I'm only taking out 100 Skittles, which is not big enough to substantially change these percentages as I march along, okay? That's the idea. I'll revisit this later. N, is there a set number of trials? Yes. My sample size is 100. It's fixed. And we're saying the probability is remaining essentially the same. You know, again, I just mentioned that we're treating it as essentially the same, okay? Number 2. We're going to put this into the applet. So open your applet up. Binomial distributions. 100 Skittles. The probability of getting a green Skittle is 0.20. Plot the distribution. There it is. And that's what is on your on the notes. You can see there the average is 20 and the standard deviation is 4 on the bottom there. Okay, 20 and 4. Great. Number 2 says, Wilcox will be disappointed if he got 11 or less green Skittles. Use the applet to find this probability. Okay, and then shade it in. Remember, you can just put, he would be disappointed if he got 11 or less. So I'm going to say at most 11. Because that includes 11 and goes down. It shades it in. Whoops, I just messed that up. Let me get rid of that. At most 11. Okay, there we go. That's shaded, and it's about 1.26%. Okay, if you shaded it on your graph, you know, we're doing like this pretty much. Now, if you did the calculator, it would be binomial CDF. 100 trials, that's N. Probability of success is 0.20, that's P. And we want 11 or less, so I do that. You can do that in the calculator, and that would give you the 0.0126, which was 1.26%. To remind you to show your work, you would have 100 C11 times 0.20 to the 11. The probability of failure is 80% of not getting a green, and that would have to happen 89 times, right? Because these two always sum to 100. Then I'm going to show one more. He would be unhappy if it was 11 or less, so now I'll go down to 10 green Skittles. 20% of them are green, that's P, right? This is like P and 1 minus P. You get 10 green ones and 90 not green ones, and then dot, 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 and that will equal my 1.26%, okay? What is the approximate shape of this distribution? Well, it is approximately normal. Or you can also throw on there, it's symmetric. Doesn't it pretty much look like there's a line right down the middle and it's symmetric on either side, bell curved? Now here is a condition called the large counts condition. Essentially it is saying this: if my sample size, it's 100, if my sample size gets larger and larger, at some point we will be able to say that this is approximately normal, okay? And the cutoff is this requirement right here. If NP is greater than 10 and N times 1 minus P is greater than 10, the sample size is large enough for the distribution to be approximately normal. Maybe I should say to be considered approximately normal, all right? Also, some other ideas is, isn't N times P my, N times P are my successes, and N times 1 minus P are my failures. So once I get to the point where both my successes and my failures have eclipsed 10, that's large enough to be considered normal. Let me go back to the applet and explain this. So let me backtrack. Let me change the sample size to something smaller. Let's say I was only collecting 10 Skittles. Does that look like the bell curve? Nope, it looks skewed right, okay? Because have I collected enough Skittles to have 10 successes and 10 failures? Well, no, I've only collected 10 Skittles. What if I did 15? I still see a skew there. What if I did 20? The skew is still present, okay? I have to keep going until N times P, right? Until N times P is at least 10. So what I have right here on the screen is I have 20 times 0.2. 20 times 0.2. That's only 4. So I'm not even close enough. I need to get to, if I have 50, this here is enough to be considered approximately normal because 50 times 0.2 is 10. I've gotten to the point where I would expect to have 10 successes. And then I would also expect to have at least 10 Skittles that are not green. 10 and 40, right? Makes my 50. So this is the minimum sample size required to be considered approximately normal. All right, back to the notes. What is the formula for the mean of a binomial distribution? Look in your green packets, everybody. The mean of a binomial distribution is 1 over, that's geometric. Phi gets n times p. So that would be 100 times 0.20. So that's 20. The formula for standard deviation is square root of n times p times 1 minus p. Just a quick reminder, where is this? It's in your formula sheet right here and right here because it's binomial. Okay. That would be 100 times 0.20 times 1 minus 0.20, or you could just put 0.80. And this was 4. The applet actually gave this to me earlier. Okay. Number 6, redo the problem. Number 2, redo this, treating it like a normal distribution. So here's the thinking. This is the answer, treating it as a binomial distribution, which it is, 1.26. But since we satisfied large counts, we can now treat it as if it was approximately normal and use the normal curve to approximate the answer. So the curve would be labeled with 20 in the middle, and it would go up and down by 4, like 24, 28, and so on, 16, 12, 8, just filling it in like that, right? And what was Mr. Wilcox upset about? If he got 11 or less, he'd be bummed. Okay, so where is that on my normal curve? Roughly 11 is right here, right? 11 Skittles. 11 or less, and he'd be upset. The binomial approximation had this shaded percentage as 1.26. They're going to be close, but they're not going to be identical, okay? So to do the normal curve, you need to get a z-score. So the z-score for 11 is the value minus the mean divided by the standard deviation. That's negative 9 over 4, which is negative 2.25. Okay? You can look at table A. I haven't done that in a while. Let's look in the green packet and find this. Table A, you can find a z-score, negative 2.25. That would be negative 2.2, and then here's the 5. There you go. So we've got 0.0122%, which is almost exactly what we had, right? So table A gives us 0.0122, or 1.22%, which, look how close that is, folks, right? This is the whole point. These are almost identical. So meaning that, was it reasonable to say that this is approximately normal? Yes, it was reasonable. Look how close the answers turned out to be, okay? You could also do your normal CDF button, if you were wondering about that. Normal CDF, negative 99, negative 2.25. Remember, it's lower and upper, like that, because my lower is way down here at negative 99, and my upper is negative 2.25 for my z-scores. All right, number 7. I want to circle back to this idea right here about independence, okay? What if the party size bag was only 20 Skittles and the sample size was 10 Skittles? So I'm shrinking the sample size. How many in the bag would we expect to be green? Well, it's still binomial, right? So this is N, this is P. No, that's not P. That's how, oh, back up. Like this is N. This is like the population, the whole bag, right? So the expectation is the average. So that would be N times P, which would be 10 times 0.20, which is only 2. You would only expect 2 green Skittles, right? Which isn't that much. If the sample size was 10 and the Skittles were not replaced, is the independent requirement of bins met? And the answer is no. Let me say the nitty-gritty. No, it's because 10 is greater than 10% of 20. Okay? Meaning I'm taking away 10 Skittles? That's half the Skittles. This is going to have a very significant impact. There's the bell. A very significant impact on the probability of getting a green. So if you go to draw number 1, let's say you got a green, okay? The probability of getting a green is 2 out of 20. My bad, sorry. Oh, sorry. I screwed this up right here. I gotta go backwards. I did the expected binomial. I didn't do the expected number of greens. I'm sorry. It's not this. Sorry about that. This would be 20 Skittles, and you expect 20% of them to be green. So that would be 4. So there are 4 Skittles in the bag, okay, on average. So the probability of getting a green Skittle for this first draw would be 4 out of 20, which is exactly 20%, okay? But now draw number 2. Let's say you want to get another green. Well, now there's only 3 greens left, and we're down to 19 Skittles. And 3 out of 19 is down to 15.7%. So that's a pretty substantial change. Why is it such a substantial change? It's because I am taking a large percentage out. The percentage I'm taking is much larger than 10%. Let's just drive this point home. What if my third draw was green again? Right? Now there's only 2 green Skittles out of 18. My probability of getting green is continuing to really, really change. 0.11. I should write these all the same way. 0.157, okay? It went from 20 to 15 to 11. It almost got cut in half, folks. So is the result of the first draw affecting the second draw and the third draw? Yes, it is. Why is that happening? It's because my sample size is half of the population. That's why. So that is where this 10% condition comes from. If my sample is less than 10% of the population, then I am not changing the probability significantly from one draw to the next draw. Okay, and I've summarized that right here. The 10% condition for independence. If the sample size is less than 10% of the population, we can assume independence, even if there is no replacement of the green Skittles. That is a very important thing moving forward. You can also say it like this. If you take 10 times the sample size. If that is less than the population, it's independent. This is another way of saying if n is less than 10% of the population. Okay. Quick notes. Large counts, I addressed higher up. If the sample size guarantees that you should expect 10 successes and expect 10 failures, then you can use a normal distribution. Okay, and this is important. It is what you expect. It's not what actually happened in the collection process. It's what you expect to happen. Okay, and then if you can use the normal distribution, then you can model it with a normal curve like we did. Okay, you can find the average, which is n times p, and the standard deviation, which is that formula, which is what we did right here, folks. This is what we did right here. We got 20, put it in the middle of the curve, got 4, and I counted up by 4s and down by 4s. I modeled it with a normal distribution. Then I found my z-score and used table A. Okay? That's the lesson. Have a great night, or day, or morning. Bye-bye.